So, it is my honor and pleasure to introduce Vano. And today, Vano will be talking to us about the legend of question 6. He's a first year MMDA major, and he's excited to tell us about this very difficult problem. So, please.
Hello everybody, my name is Vano. I'm a first year math major, and today I would like to talk about the legend of the question 6. So before I do that, I want to introduce what competitive mathematics is and what it's really about. So competitive mathematics is
Where did it go?
Click on,
Oh, there. Now go.
click on this.
okay. Thanks. So competitive mathematics is a subset of mathematics which focuses on competitions and Olympiads. And most of the time, high school students and university students participate in those Olympiads. So an Olympiad is the structure of the Olympiad is the following. So Olympiad organizers give students some sheets where there are some problems, and the students should solve the problems in some amount of time. It can be 2 hours, 4 hours, and so on. One of the most prestigious math Olympiad ever is the IMO. It means International Mathematical Olympiad. And the structure of it is as follows. So there are 2 days, and on each day, participants are given 3 problems, and they're given 4.5 hours to solve those problems. One of the hardest problems that was ever on the IMO was 1988 IMO problem 6. And before it was selected, it was checked by members of the problem selection committee, and nobody could solve it. Even it was sent to 4 of the most brilliant number theorists in Austria, and they worked on this problem for 6 hours, and they could not make progress. They could not do anything. Even a Fields medalist was stumped when he saw this problem. But surprisingly, 11 high school students managed to give a solution of this problem during the competition. So let's see what the problem is. It's a little number theory problem. It's just 2 lines, and the statement is very easy to understand. It says that if AB are positive integers, such that AB plus 1 divides A squared plus B squared, then A squared plus B squared over AB plus 1 must be a perfect square. I mean, everybody can understand the statement, right? And no one would think that this is some insanely hard problem. So let's see the solution. But before we do that, let's explain what infinite descent is. So infinite descent is a mathematical technique that's used to solve a lot of problems using the arguments of descending infinitely and reaching some contradiction. It's just another mathematical technique, just like induction, right? But it's used in a different way than induction. And we'll see what it really means by solving some examples. So first example. So let's consider this example. So solve the equation x cubed plus 2y cubed plus 4z cubed equals 0, where x, y, z are integers. Okay, let's go to the solution. And so okay, solution. Let's consider this equation mod 2. And by doing so, we will get that 0 is congruent to x cubed mod 2. It means that x cubed is divisible by 2. And since 2 is a prime number, it means that x must be divisible by 2. So if we write x equals 2x prime, and then we write this equation, we will get the following equation. Now, you should be able to see some kind of similarity in the structure of this equation and the previous equation, and they really are similar. And we can apply the same procedure one more time to deduce that y is divisible by 2. Then we will get that z is divisible by 2, then x prime is divisible by 2, and so on. We will go on infinity. And this will leave us with the only choice that x, y, and z are all three of them equal to 0. Okay, so this is one example of infinite descent. Now let's do another. Fermat's last theorem. I'm sure that most of you know what Fermat's last theorem is. It was an unsolved problem for a lot of time, like 350 years, and Andrew Wiles was able to finally solve it after 30 years of research and hard work. And we're going to consider the case for n equals 4. And let's try to prove it. Okay, let's rewrite the equation as follows. So instead of z squared, let's write t, and let's prove that this equation has no solutions. Okay, so let's take some. So let's assume that it does have solutions, and let's take a solution where t is minimized. Okay, there's a well-known fact in numbers theory which describes the solutions, the form of the solution of Pythagorean triples, and it says that x squared plus y squared equals z squared implies that xyz equals a squared minus b squared, 2ab, and a squared plus b squared. So with this information, we get the following system of equations. So x squared is 2ab, y squared is a squared minus b squared, and t is a squared plus b squared. Now let's look at second equation, right? We see that y, a, and b satisfy Pythagorean, they are a Pythagorean triple, right? So they should satisfy this condition. And we know from the above described fact, we know that a, y, and b should be of the following form. This. Okay. Now let's look at this equation. Since we know that x squared equals 2ab, which is 4 times c times t times t squared plus d squared, and c, d, and c squared plus d squared are co-prime. So if they're co-prime, it means that c must be perfect square, d must be perfect square, and t squared plus d squared must be perfect square. In other words, this system should be true. Okay, but let's look at first two and last equations, right? What does this give us? It gives us the following thing. So if this is true, then e to the 4 plus f to the 4 equals g squared. Now, let's note that t is greater than a squared, which is greater than g. So we get an infinite descent. And why is this so? Yes?
Yes. Why do we get this infinite descent?
Because when we first started with this equation, our assumption was that t is the minimal solution of this equation. Okay, so if we assume that t is minimal solution, then we apply some valid steps, we will end up with this equation. So if we assume that t is a minimal solution, we find a solution which is smaller than t. But this gives us contradiction because such thing cannot happen. Yep. And now let's focus on Vieta's formulas. François Vieta was French mathematician. So let's solve problem 6. A squared plus b squared over ab plus 1 is the square of an integer. First, assume the statement is wrong, with k not being a perfect square. Then replace a with x and rewrite the equation as this. Then a is a root of this equation by assumption. And Vieta tells us that if we plug in a, get the following equation. Bound this from above by b squared over a, which is bounded by a, leading to an infinite descent. And I would like to go one step further, and let's talk about the geometric insight. So if we rewrite the equation, we get that the following equation represents a hyperbola. Okay. Now let's think about this. So if we take any solution to this equation, we can apply our Vieta jumping procedure to any solution until we get to the solution of the form square root of k 0. Okay, so we can just take solution, count to a smaller solution, then go to a even smaller solution until we get to the point square root of k 0. Okay, now we can think about this and we can notice that we can do something interesting with this. So if we know that any solution converges to solution of the form square root of k 0, then we can just go backwards, right? And so we can just start from the solution of this form, and we can go backwards to reach every solution to this specific k. And the idea is the following. So this is what our normal Vieta jumping looks like. So we start from this solution, then we go to this solution, then we come back, then we go, and then we end at this one. Okay. Now we need to formally describe it. And another question is also, do we always see integer coordinate points, right? Because we might start from some place, for example, from here, right? And we will go upwards and until we hit this graph again. But how do we know that it's gonna have integer coordinates? For this, we're gonna do the same. So if k equals this thing, let's take some solution, capital A, capital B, and let's replace A with X to get this equation, right? Now, what should X2 satisfy? It should satisfy the following. So X2 will be K times B minus A. And from this inequality, we get that X2 will be greater than B. So it means that from a smaller solution, we can jump to a small solution which is larger. Okay, but this inequality is true for k greater than 2. Now, natural question to ask is what happens at k equals 1? Well, at k equals 1, k equals 1, and we get this equation. So if k equals 1, we're solving this equation, which simplifies to this. So this condition provides a big restriction on A and B, and it leaves us with finitely many cases to consider. And this is what the graph of it looks like for k equals 1. So, and these points correspond to all solutions of this equation. Okay, so it's nice that we have discussed this case, and now let's discuss other cases. So what happens at k equals 4? If k equals 4, we get the following graph. So in this case, we can start from the solution 0, 2, then we move right until we hit it at 8, 0, 8, 2, sorry, and then we go up until we hit at 830. And we continue this process to find all solutions to this equation where k equals 4. We can do the same thing for k equals 9. So in this case, we will start from the solution of 0, 0, 3. We will go right until we hit the graph and then continue this procedure. And this way we have algorithmically found all solutions to this equation, which is a nice thing. So now to finish this talk, I would like to say that every hard problem has some solution, right? And you don't have to be a Fields medalist or Terence Tao to solve it. And I mean, even very smart people can not be able to solve it, but there might be some elegant solutions. And nobody knows if there is an elegant solution until one finds it. And you can be the one who finds it, and you should not give up, and you should try your best to solve the problem, whether it's in math or some other discipline. So we should all try our best. I would like to leave you some bonus points, and you can use like see how you understood Vieta jumping. And lastly, I would like to move on to Q&A session. Thank you.
Really nice talk. So before anyone asks questions, I just want to steal this the very beginning. We said we talked about Terence Tao. I think he was at the Olympiad, right?
He was 13 years old, but it's still Terence Tao.
Yeah, I think he could solve it. That was
Yeah.
very cool. Yeah. So do you have questions in this week?
Yeah, actually, very early on, when we were talking about infinite descent.
Okay.
Yes. Yeah. Yes. Right here.
Okay.
You like. Wait, no. Is it this slide? It's the slide where you said there was a contradiction.
So it's the end of the proof.
Yes.
Oh, okay. It's step 4. Yes.
So, no, I don't think it was this slide. I think it was earlier. And you said something yielded the contradiction, and I didn't quite understand how that is.
Maybe this one.
This one.
No, it's a contradiction because he finds a solution that is smaller than the original solution that he had, but he assumed that t was a minimal solution. And so if you find a solution, yeah,
Yes.
And so if t is a minimal solution, then I can find the g, which is smaller than t, which does not make sense. So if it doesn't make sense, it's not true. So we find contradiction.
But you have observed that.
Okay, I have not thought about that case, but you can think about it. So if x2 is same as a, then we have some condition. So we have conditions that 2 times a equals k times b. Then
We have also that the constant term is the product. So b squared minus k will be a squared. So basically it will be that a squared.
so b squared minus k equals a squared.
Mhm.
B squared is a squared plus k.
Mhm.
Uh, But we had assumptions that a is greater than or equal to b. I'm thinking if it violates it, something to a will work from a equal.
Yes, then we have that a squared equals 4 squared.
Yes, or no.
Because
Yeah.
is b squared minus k.
Yeah. B squared is a squared plus k, and a squared is greater than or equal to b. So yeah, such case cannot happen or might happen. So it's another discussion.
But it seems like now we solve it because if a is greater, but here we are saying that a is smaller.
Oh yeah, yeah. So we get the contradiction.
We solved
Yeah.
it, but that's a lot of points.
That's how we solve most of it. Okay, so this is our solution. With help of Professor Rosin, we solved the problem.
So sorry. Okay, so you said if it's true as contradiction, we go to minus infinity. Why would that be a problem?
It will not go to minus infinity because we're dealing with positive integers. So t in our case is positive integers, and positive integers have lower bound. So
So you can keep going lower and lower. And
There's no more
Those
place.
is needed, so-
so more questions for this week.
So in this Vieta process, so you have one pair of numbers, and if you go step up, then the smallest number becomes the biggest.
yes, yes.
So that's the case when we stay in one place, it's not possible. So a fixed point is not possible. I mean, when x1 is equals x2 is not possible because of this inequality. So this process never stops.
Okay, any other questions?
Yeah, I think the process does never stop. So you have for the Vieta setup, for the Vieta jumping setup, it gives you an infinite family of solutions.
Yes.
So it characterizes. So even when you don't have, let's say, a proof by contradiction in some sense, or let's say if you don't use infinite set, if it doesn't rule out the existence of solutions, it characterizes them. So this is at least what you can hope for it. So That's, I guess that was very good. This is more of a remark and less than of a question. But yeah, I thought that was very interesting.
Yes.
Sorry, just at the very beginning when we were solving the equation with the x cube plus 4 plus
Yeah.
6 cube is equal to 0. You came to the conclusion that the solutions are all variables in the form of the two times something, right?
Yeah.
Okay. What I didn't get is that I could easily find the solution which has because like due to the fact that two of the coordinates are multiplied by 2, you could find something that is odd and even. It will work. That's why I didn't get.
So can you repeat?
So basically, due to the fact that in the equation it's like x cubed plus 2y cubed plus 4c cubed is 0, and since like two of the terms are multiplied by 2's power or something, which means that if you're using like I don't know like
Two to the power something or like
two because it is 2 and 2 to the power of 2. That's what I mean. No, it's not about this. Like it's just about for example, if you take as a solution, I don't know, 2, 3, 7. 3 and 7 are not in the form of 2 times something, and so it's very easy to the equation. That's why I was confused.
2, 3, 7. So if we take x, y, z equals 2, 3, 7.
Yeah. 3 and 7 are not all the even numbers, but still it's a solution of the equation.
Which equation?
This.
Did you compute this?
Well,
The should at least one negative, otherwise.
it will not satisfy this equation.
No, but it's in no, what is modulo?
You don't, yeah, if we're talking about modular case, well, okay, y and z can be 3 and 7, okay, at this moment they can be, but at the next stage they cannot be 3 and 7.
So the question was equal to 0.
What?
Okay, no, I just want I thought the question was like congruent to 2.
Oh yeah, I mean, this is congruent to 0, not 2.
Yeah,
Well, 0 is congruent to 0, but
yeah.
yeah. And so this part is congruent to x cubed, and from this fact we find that x is divisible by 2.
Yeah.
And then we find that everything is divisible by 2.
Yeah. Thank you very much.
Yeah.
More questions?
Any hints how to solve those problems?
A lot of practice.
Maybe you could do
in some work.
Is it also by Vieta Jumping?
Which one?
The bonus problems?
Oh, yeah. Yep, I have solved first problem, and it uses Vieta Jumping, but I have not. Oops, sorry. Okay, so
You can move the mouse.
first one is done by Vieta Jumping, and I mean, you can find those solutions quite easily. Well, if you want a hint, I can tell you to start by setting everything equal to 1 to find that just a single solution. So instead of ABCD, take T to find single solution, and then try to get to other solutions. Try to find other solutions. And okay, another hint is to consider quadratic equation in one of the variables. So instead of one variable, take x, and then see what happens. And this problem, I have not solved it, and I know it's hard. And
It's clear.
it's I know problem 5, so
Maybe it's the second hardest problem in the history of the Yeah, maybe it isn't. Who knows? So let's thank our speaker one more time.